Okay, permutations on a finite set. For each of the following parts, tell whether it specifies theta as a permutation on x5 subscript 5 equals 1, 2, 3, 4, 5. If not, explain how definition 1 is not satisfied. So I probably overcomplicated this a little bit by explaining explicitly definition 1. But yeah, it's this definition. It's basically saying that you can't have the same, you'll see here. It's basically like it has to be 1-to-1 pretty much. Is like what we're looking for, number one. Like that's the main thing we look for right now, is permutations. So the first one, 1 goes to 1, 2 goes to 3, 3 goes to 4, 4 goes to 5, 5 goes to 1. This is not a permutation on x5, as 1 appears twice in the listing, and 2 also does not appear at all. So to be 1-to-1, it has to have what it goes into has to appear once each. Each number that's possible to appear basically is one way of saying it has to appear once on the output, and you input each one to a specific output basically. So as you can see, yeah, and this is basically the output. 1 appears twice, 1 goes to 1 and 5 goes to 1. So this does not work out, this is not a permutation. B and C are permutations though. As you can see, 1 goes to 5, 2 goes to 1, 3 goes to 2, 4 goes to 3, and 5 goes to 4. 1, 2, 3, 4, 5, and 5, 1, 2, 3, 4. It works out. Finally, 1 goes to 1, 2 goes to 1, 3 goes to 1, 4 goes to 1, and 5 goes to 5. Permutation, obviously the same reason. Express each of the two permutations on x2 equals 1, 2 in the 2-row form. 1, 2, yeah, so A, B, basically, yeah, A and B basically have to, this is very simple. All you do is put, this is another problem. It's a problem in the book, but I think this would be 7. Regardless, it works out. But yeah, basically it was number 3 though here. In the 2-row form, 1, 2, A, B. So we have to put the x2 equals 1, 2. This the permutation. You have to find the two permutations. So it's 1 goes to 1, 2 goes to 2, and 1 goes to 2, 2 goes to 1. I'm using the 2-row form here. It even specifies that. In general, it doesn't matter what form you use really, as long as it makes sense. But I try to go by what it expects it to be in. You know, at least when it's directly asked about it, I put enough. Yeah, basically just 1 goes to 2, 2 goes to 1, and 1 goes to 1, 2 goes to 2 are the two possible permutations. Let alpha and beta be the permutations on the set 1, 2, 3 given by alpha is 1 goes to 2, 2 goes to 1, 3 goes to 3, and 1 goes to 2, 2 goes to 3, 3 goes to 1 is beta. Find the permutations gamma on 1, 2, 3 such that gamma x equals z whenever alpha x equals y and beta y equals z. Yeah, and this is basically what will be later on known as multiplication of the permutations. But otherwise, then it's a composition basically as well, composition function, essentially, what you know from basic algebra, composition function. So I write them as a 2-row form to make it simpler. And alpha 1 equals 2, beta 2, then you take that output and put it in this beta 2's input, and then goes to 3. You get gamma 1 equals 3. Input of A and output of beta, what gamma's input is A's, and then beta is the output. Alpha 2 equals 1. So alpha of 2 goes to 1, and then 1 goes to 2. So gamma of 2 equals 2. Alpha 3 equals 3, so 3 goes to 3. 3 goes to 1. So gamma 3 equals 1. So gamma is equal to 1 goes to 3, 2 goes to 2, and 3 goes to 1. In either of these forms appropriately. Find the permutations. Delta, I'm pretty sure that's a delta, on the set 1, 2, 3 such that delta x equals z whenever beta x equals y and alpha y equals z. So this is sort of a reverse using the same alpha and beta. See? So yeah, same thing as before. So this time the beta, we go with beta to alpha basically, so because gamma x equals z, so beta x equals y and alpha y equals z. So 1 goes to 2, 2 goes to 3, so that's why beta, okay, wrong. Beta, as I showed on the paper, beta 1 goes to 2, 2 goes to 1. So gamma 1 delta equals 1. Delta 1 equals 1. Then beta 2 goes to 3, and then 3 goes to 3, so delta 2 equals 3. Then beta 3 goes to 1, 1 goes to 2, delta 3 equals 2. 3 to 2, 2 to 3, 1 to 1. So 1 to 1, 2 to 3, 3 to 2 is what delta is, or in this arrow form it's 1 goes to 1, 2 goes to 3, 3 goes to 2. Now this one, let alpha equal 1, 2, 3, 4, 5, 6, and then 6, 4, 1, 2, 3, 5, 3 on the bottom row. Rewrite with the columns rearranged so that alpha equals 1, A, B, A goes to B, B goes to 1, 2 goes to C, C goes to 2, and D goes to D. And you just have to observe this and keep the columns correct. So only one of these starts with 1, and 2 you can outright pick out there what it starts with. You have to follow the patterns. If 1A goes here, then AB has to be, so 6, because that would be A is 6 then, so 6 has to go next to it, and since 3 is B, so B to 1 is 3 to 1, obviously enough. Right, that gives you confirmation. Then you'd pick, it's always going to be 2 here, so 2 to 4, so C is 4, then C to 2 will be 4 to 2, and then D to D is the only one that goes into itself, 5, 5. And give the diagram for the permutation alpha of problem 11, so this problem. So we have it drawn out in the form that makes it easy to see. So 1 goes to 6, 6 goes to 3, 3 goes to 1, and then 1 goes to 6, so that ties it up. So I draw a triangle sort of here, and the arrows go into each other. 1 goes to 6, 6 goes to 3, 3 goes to 1. 2 goes to 4, and 4 goes to 2. So 2 goes to 4 again. And 5 goes to 5, so just a circle. And that's it for the introduction on permutations on a finite set.